Now that we've explored a lot of different topics and applications involving multivariable differentiation, like we learned about partial derivatives, tangent plane approximations, chain rule, optimizing Lagrange multipliers, gradient, directional derivatives, all this sorts of stuff. We want to explore integration in just as much detail as well, right? We now want to talk about integration of multivariable functions. And so let's recall how we defined integration in the single variable case. The single variable integration, right? We don't have to be super rigorous for right now. This is just kind of so we remember what technique we use to define integration. We wanted between like two vertical lines, say like x equals a and x equals b, we wanted a way of calculating the area between the curve here and the positive x-axis, right? Or between the x-axis and this curve, some y equals f of x. And we learned that the area here is equal to the integral from a to b of f of x dx. Now, how did we calculate this integral? We started by taking approximations, right? We introduced a partition of the interval, of the closed interval AB into like x1, x2, xi, et cetera, right? Where we could say like a was x0 and b is xn. And then we took rectangle approximations, right? We could take like right endpoint or left endpoint or something like this. But the point is we started by taking approximations and getting the area of these subrectangles. And then taking the area of the subrectangles, so we took the sum of the area of the subrectangles, right? And then to define the integral, we said that the integral was the limit of the sum of the subrectangles, right? And this gave us an exact formula for the integral, right? And again, this is very sketchy. We'll go through it in the rigorous way for double integrals, but we want this same idea of approximation via like subrectangles here to get an approximate area. So let's consider a rectangular region. So let's say that we have some function f of xy, and let's let this be continuous over region R, and let's let R be the set of points x, y in R2 such that x is between A and B and y is between C and D. So we get something like this. And we're going to introduce some new notation here. We're going to use the Cartesian product. And we write this region R as AB cross CD. And this region R, what it looks like is you have two values AB, two x values A and B, you have two y values C and D, say here, and then you're looking at the region bounded by these four lines, and you notice you'll get a rectangle. And we write this as AB cross CD. And so this region R is the rectangle between x values A and B and between y values C and D. And now this is our domain, right? And so what we're looking at now when we're talking about integration is if we have some rectangular region R, which is AB cross CD, in the xy plane, something like this down here, right? Then you can imagine that above this, we have some surface. We have some surface defined by F, right? So we're looking at like this surface over this region R, right? So here's R down here in the XY plane, and you can imagine like above it, you could imagine hanging like a sheet above it. And then like part of this sheet over the region R is the part of your surface that's above this region. And so this surface would be given by like Z equals F of XY. And now you'll notice with the region R here, this rectangular region in the XY plane, and then this surface up here, we can think of this as bounding almost like a prism here, that is kind of cubic on the bottom and sides, and then on the top, it's not a perfect cube, but the top of the cube is defined by, or it's shaped by whatever the function f of xy is giving as a surface, right? And so now what an integral or a double integral of this function will give us is the volume of the region above, or so let's say the volume of the solid above R and below Z equals f of xy. So again, think about this region, this solid here, as like a box where the bottom of the box is the region R and the top of the box is the function, right? It's the surface, however the surface is behaving over the function. And so how do we calculate, how do we estimate this volume, right? Well, we can do something similar that we did with the single variable case. In the single variable case, we took a partition of our domain, right? Which was here, the domain was the interval AB. And we partitioned it with this partition like xn or xi, right? We can do something similar here. Let's partition B into, let's say, M subintervals. And then let's partition CD into N subintervals. So if we have our region R here, say, we're looking at x equals A to x equals B, and we want to partition this M times, so like x1, x2, etc., up to, let's say, like xi minus 1, xi, etc., etc. And then we'll let like A be x0 and B be xm, right? And then we're also partitioning the interval along the y-axis as well. So here's C to D, and so we partition this into like y1, y2, et cetera, say like to yi minus 1, yi, et cetera, and then where C will be y0 and D will be yn, say. And now we can kind of look at these partitions as, well, in each kind of along the interval A to B, it partitions that interval. But if you extend these partitions, right, and so these should be perfectly vertical, and they're not, right? And then you can extend the partition of your Y interval as well. And now we get a family of subrectangles here. And so you could look at like maybe like the sorry, I want to index my y interval with j, right? Because they have different indices, right? I is running from 0 to m, and j is running from 0 to n. Excuse me. And so here we can think about like the subrectangle that's given by like the xi and yj partition as like r sub ij, right? And now, how do we want to use this partition, like this r sub ij, all these subrectangles here, right? So like this bottom one down here could be like R11 because it would be like the first rectangle in each partition, right? How do we want to use like this collection of subrectangles in our region R? How are we going to use this to estimate volume, right? Well, if you think in each of these subrectangles, we can pick a kind of a test point, if you will. So we could pick like a test point, and let me write it in blue. And we're going to call this test point xij star and yij star. And so we're going to pick a test point in every single region, wherever it may be, right? We just require that in the ij rectangle, the point, like the point xij star and yij star live in the ijth rectangle, right? And so we pick a test point for every single sub-rectangle that we get here. And when we do this, we can apply the function to this test point. And so if we pick a test point here, let me use yellow in there. If we pick a test point like xij star, yij star, and if we plug it into the function, then that's going to give us some value on the surface, right? This is going to be f of xij star, yij star. And we can use this as an approximate height of like a prism where the volume of this little prism is given by the base, right? The volume of this prism is going to be base times height, where the base is the area, let's say area of Rij, and then the height is going to be, well, whatever the value of the function is at this test point, that's going to be the height of this like thin, very small pencil-like prism, right? And so the height here is going to be, and so let me write, this is even like volume ij, right? Because this is the volume of like the prism over the ijth rectangle, right? And so this, then the height is f of xij star yij star. Okay, and then we can do this for every single rectangle, right? We can do this for every rectangle Rij, right? And so what are we going to get here? What I'm calling Vij here, let me call this now, let me use more formal notation here for calculating the volume. What we've said is that delta V here, or this very, very small volume over the Rijth rectangle, is given by the area of the base which we'll call delta A times the height, right? And so what is delta A? Well, delta A is going to be the area of the ijth rectangle. And the area of the ijth rectangle is going to be length times width. Well, the length is the subinterval due to the x partition, and that length we'll call delta x. And then the height is going to be due to the length of the subinterval of the y partition, which we can call delta y. And so the area here is going to be delta x delta y, and then times the height, which we said what the height would be, right? The height is going to be the function at our test value inside this rectangle. And so this is times here, f of xij star yij star. And so this is a formula for the volume of just one little piece, right? Like this is the volume of the prism extending from the ijth subrectangle. And so total volume can be approximated approximated, right? So now we're looking at the entire volume of the big prism here, kind of the entire region that is above R and below the surface. This can be approximated by taking the sum as I goes from 1 to m and as j goes from 1 to n of f of xij star yij star delta x delta y, right? This gives us this double sum here is just summing up. So we do this construction for every single subrectangle down here in R, right? And so we get a bunch of these little prisms here where the base is the area of the Rij, and then the height is the function. We take the double sum, add all those up, and that's approximately the volume of this region. And now, if we take these partitions to be arbitrarily fine, like meaning n gets very, very big and m gets very, very big. And so it's super fine partitioning, like you're cutting up your intervals a lot, right? Well, if you let these go to infinity, then this approximation becomes exact. And we get that v is the limit as m and n approach infinity of this double sum from I equals 1 to m, j equals 1 to n of f of x ij star y of ij star dx dy. Whoops, delta x delta y. Okay, and again, it's more convenient of this actually to consider this as just area, right? So this is just change in area. And now we have a definition of the integral. The integral over the region R of the function f of xy is exactly the limit as m and n goes to infinity of the double sum from I equals 1 to m, j equals 1 to n of f of xij star yij star dA. And so this is how we define the double integral. Okay, and so recall then that the double integral over the region R of f of xy dA, well, we know what dA was, right? We know that delta A was equal to delta x delta y. So that means when it becomes infinitesimal, we get dA equals dx dy. And so we can write this as a so-called iterated integral. And we may write this as the integral from x equals a to b and y equals c to d of f of xy dx dy. And so what does this mean? This iterated integral, what this means is you take the integral of f of xy with respect to x first, and then you take the integral of that integral with respect to y, okay? And then notice that dx dy would be the same as dy dx. And so we have a theorem that's attributed to Fubini. And Fubini's theorem says that it doesn't matter which order you integrate. If you're looking at an iterated integral, then it's intrinsic, whether you integrate with respect to x first or with respect to y first. And so thanks to the mathematician Fubini, we know that this is the same as the integral from y equals c to d of f of xy, but we switched the order, right? So now it's dy dx, and then x equals a to b. And here again, the iterated integral means you integrate. You always integrate inside out when you're looking at multi-integrals. So when it's a double integral, and when we even look at triple integrals, right, for functions of more variables, then when we're looking at iterated integrals, we always work inside out. And so this is a construction for the definition of a double integral over a rectangular region. So let's see an example, right? That's a lot of kind of analytic construction here, and there's not much hands-on, right? So let's see an example. Let's compute double integral over the region R of f of xy dA, where f of xy equals x and R equals, it's the rectangular region 0, 2 cross 0, 1, right? And so this region R is 1, 2, 1, so it's this rectangle here, right? It's 2 units in the x direction, 1 unit in the y direction, and it can be this entire region here. So great. What do we see here? Well, the double integral over R of x dA, we know by Fubini, we can express it as an iterated integral, right? If we express this as an iterated integral, this becomes the integral, and I'll do x first, right? Again, by Fubini, we can do this in any order we want. I'll integrate with respect to x first. So this is from x equals 0 to 2, because this is our x bounds, and these are our y bounds, right? So y equals 0 to 1. Then we're integrating x dx dy. Okay, so we have integral from y equals 0 to 1. And now we're taking this integral first, right? And this is just a standard single variable integral. So we get 1/2 x squared from 2 to 0 dy, which is the integral from y equals 0 to 1 of, well, if we plug in 2, we're going to get 4 over 2. So that's 2 and then minus 0. So we get integral from 0 to 1 of 2 dy, right? And this is the integral. Well, if you integrate 2 with respect to y, you get dy, or 2y, excuse me, from 0 to 1, which is just 2. So you can see the integral of x over the region 0, 2 cross 0, 1 is just 2. And here's an example of how we can use Fubini's results to express this as an iterated integral, and then just do integration one at a time. Okay, let's see maybe a less trivial example, maybe one with both variables, right? Because this one just had the variable x in it. And so once we came to integrating with respect to another variable, it wasn't too difficult. Let's see another example here. Another example would be, let's compute the double integral over the region R of xy minus 3xy squared dA, where R is the region 0, 2 cross 1, 2. So, and just to get an idea here, this would be 0, 2, and then cross 1, 2. So this would be this rectangle up here, right? Because x can vary from 0 to 2, but y can only vary from 1 to 2. And so we get this rectangle that's lifted 1 unit off the x-axis here. This is our region R. And thanks to Fubini, we can write this as xy minus 3xy squared dA. And this is equal to, and now it doesn't really matter what we integrate with respect to first, right? I think either way it'll be pretty similar. So this is x goes from 0 to 2, and then y goes from 1 to 2 of xy minus 3xy squared dx dy. And now, when we are integrating with respect to a given variable, we still treat all other variables as constants, because the integrand is the taking the integral is how kind of the same as what we do when we take an antiderivative, right? And so when we take partial derivatives, we know we need to hold other variables constant. If we're looking at like x, we hold y constant, right? This same idea applies for integration. And so when we integrate with respect to x, we need to hold y constant. And so how do we integrate xy while treating y as a constant? Well, that would be, so we have the integral from y equals 1 to 2. And if we integrate with respect to x, in the first term, we're going to get 1/2 x squared y, right? Because the constant's along for the ride when you integrate. And then we have 3xy squared here. So when we integrate this with respect to x, 3y squared is all a constant. And so this is going to be 3/2 x squared y squared. And we're evaluating this at 2 and 0, and then dy. So, well, let's plug in 2 and plug in 0. We notice if we plug in 0 for x, we get 0. So we only have to worry about what happens when we plug in 2. So this is the integral from y equals 0 to 1. If we plug in 2, we're going to get 4 over 2. So 2y minus, and then we plug in 4 over 2. So minus 6y squared dy. Right? And so now let's copy this down. This is the integral from y equals 0 to 1, 2y minus 6y squared dy. And now at the last step, it's always a single variable integral at the last step, right? Because we removed all x's. Right? And so like your answer should always be a number. If you ever do a double integral or a triple integral and your answer has variables in it, you know you've done something wrong, because this is always giving us volume, right? And volume is a number, not a function, right? You can write a function for volume of like a changing solid or something, but in general, like this is a volume that we're calculating, so the result should always just be a numerical answer, and it should not have any variables in it whatsoever. And so when we integrate here, we get y squared minus 2y cubed from 0 to 1, which is 1 minus 2 minus 0, right? Oh, what am I? Where did I pick up 0 to 1? This should be 1 to 2, right? 1 to 2. Look at our bounds here. Okay, so all the math was correct. I just copied the bounds wrong. So 1 to 2, 1 to 2, and that'll change our answer slightly, right? If we plug in 2, we're going to get 4 minus, and then 8 times 2 is so 16, and then minus 1 minus 2, which looks like we're going to have negative 12 plus 1 is negative 11. Okay, and so here's another example of calculating a double integral using an iterated integral and Fubini's theorem. So let's see one more example that's maybe a little more difficult, so that way we have a nice enough introduction to double integrals that we'll be able to start solving more difficult problems. So let's solve the double integral over the region R of x sine x y dA over R, which is the region given by 0 to pi across 1, 2 here. Okay, and so now with this as an iterated integral, this is x equals 0 to pi, y equals 1 to 2, and then x sine x y dx dy. And now this is where Fubini's theorem is important, because if I were to try to solve this with respect to x first, right? If I were to do it in this order where it's dx dy, I would have to use integration by parts here, right? So doing it this way requires integration by parts, which I don't really want to have to do unless I have to. I mean, it's not terrible. So if that's my only way forward, then it's not bad. But I can look at this and say, well, I don't want to do integration by parts if I don't have to. And Fubini tells me that I can switch the order of integration here. So what's going to happen if I switch the order of integration? What if I let this be y from 1 to 2, x from 0 to pi of x sine xy, but now dy dx? Well, what if I integrate this with respect to y, right? Now x is a constant. X is just some number that can be pulled out front if I need to. And so when I integrate, like what's the integral of cosine ay dy? Well, it's negative 1 over a sine ay, right? And so what that means here is, since x is constant, I can use this rule from the past with just replacing a with x. And so this is integral from x equals 0 to pi. I have, once I integrate, then I have negative x over x cosine xy. And I'm evaluating this from 0 to pi, right? Or no, sorry, 1 to 2. Okay, so 1 to 2, and then dx. So let's clean this up a little bit here. This is the integral from x equals 0 to pi. Notice now I have this negative x over x cancels, which is what made the switch worth it, right? This is what made me not have to do integration by parts when I'm integrating with respect to x. So it's nice to remember Fubini's theorem and say, like, if you come across a double integral that's tricky, say, okay, should I switch this to make it easier? Or even if I shouldn't, at least I checked and saw that it doesn't matter. So we have, I can pull the negative all the way out in front of the integral here. And then I have, then I have cosine xy. And I'm evaluating this from y equals 1 to 2. And so this gives me negative integral x equals 0 to pi of cosine 2x minus cosine of x dx. And now I can just integrate with respect to x. So I have negative, and then if I integrate with respect to x, I'm going to get 1/2 sine 2x minus sine x, evaluated from 0 to pi. And I can flip the order by distributing the negative. So this is going to be sine of x minus 1/2 sine of 2x. And then here I notice if I plug in pi, well, sine of pi is 0, sine of 2 pi is 0. If I plug in 0, sine of 0 is 0, sine of 0 is 0. So the whole integral ends up being 0. Now, this problem was important because it shows us that sometimes it's worthwhile to check if switching the order makes the integral easier, because it did. Right here, then, we just had to do integrals using this rule involving the antiderivative of standard trig functions, whereas had we not switched, we would have had to do integration by parts with a trig function, which is not fun. And this gives us a good stopping point for double integrals over rectangular regions. And next, what we're going to do is look at double integrals over arbitrary domains. So we could, if you'd imagine, we have this rectangular region R. Inside this region R, there's some domain D, right? And we know what the integral over a region R is defined to be, right? It's the double integral of some function dA over the region R. What we're going to do is, if we have this region D inside some rectangular region R, we can define a function g of xy that is f of xy if xy is in D, and 0 if xy is not in D. And this will give us a way of defining the integral of f, but just over this region D, where D can be arbitrarily, like the boundary of D can be arbitrarily complicated. And so that's what we'll do from here, is we'll extend our notion of double integrals, but now to more general regions.